Start from a theorem. If the codomain is a product space, a mapping is linear exactly when each coordinate projection composed after it is linear. That reduces mapping into a product to a set of independent questions. It ties back to the last section. For a linear map from coordinate n space to coordinate m space, composing the ith coordinate projection after it gives the linear functional whose skeleton is the ith row of the matrix. So when we replaced one vector equation by m scalar equations, what we were doing was reading off the ith coordinate. In algebraic terms, replacing one linear map by a set of them, which the theorem says is equivalent. Now take the case where the domain and codomain are the same V. Besides being a vector space, it is closed under composition, and composition is always associative. With the distributive laws and the scalar relation, that structure is called an algebra. The real-valued function spaces seen earlier are algebras too, but their multiplication is commutative. In Hom of V it is not, unless V is the trivial space or is isomorphic to the real line. Besides the coordinate projections, there is a second class of basic linear maps on a product, the injections. The jth injection takes a vector in the jth factor to the element having that value at index j and 0 everywhere else. Their relationship is two identities. A projection after its own injection is the identity, and after any other injection it is 0. And if the index set is finite, summing injection after projection over all indices gives the identity. An example, take a linear map from 3 space to the plane with a 2 by 3 matrix. Composing the first coordinate projection gives the linear functional whose skeleton is the first row, so the map comes apart into two linear functionals. Putting them back together uses exactly that identity. The two injection after projection terms sum to the identity, and applied to the original map, they reassemble it. In general form, given a family of linear maps out of a common domain into the separate factors, there is exactly one linear map into the product such that composing each coordinate projection after it returns the one you started with. There is a symmetric statement when the domain is the product instead. The theorem holds for all product spaces, finite or not, and in fact characterizes them. The book grants this looks overly formal, but says it helps later in more complicated situations.